My name is Martin Torrado and I work for our tech support team. In this webinar, we will talk about offline smart device applications for the new version of X Evolution 3. So, let's start from the basics. That is, what are offline applications? Offline applications are partially connected, in other words, autonomous applications. And what does this mean? This means that when I'm using my application on my device connected to the internet, when that connection is lost, I will still have my application running. And when I do finally recover my connection to the internet, a synchronization process with the centralized server's database will take place. Therefore, we could say that these applications function at all times, regardless of whether we have a connection or not, and they access local data with the possibility of executing complex logic on the device's side. Why do we have this type of applications? We do this because of exactly what we just said, because we may not always have internet connections available to us. So, my application will continue to function even where I cannot get an internet connection. We say that we make our applications more complete, and we make them more functional. And most of all, as I pointed out in the bold letters on the PowerPoints because it's very important, because we may solve a wide range of new scenarios where offline applications, instead of something desired, become a system requirement. And we have thousands of examples of this. For instance, Salesforce applications, where my sales cannot depend on whether my device is connected to the internet or not. So far then, we've found out what offline applications are and why we use them. Now I'd like to talk a little about architecture. And what better way to do that than to compare it against a model we already know about? The model of architecture of smart device applications in X Evolution 2. As you'll recall, what we had up to the X Evolution 2 was our devices with an installed application that was connected to our centralized server's database through a layer of REST services. And we connect it to obtain data and execute insert, update, delete on the server side. That was basically the architecture we had been working with up to the X Evolution 2 version. And though many things remain the same in the architecture of X Evolution 3, we will now have a database on the client side. An SQLite database, which is already pre-installed in both Android and iOS. This is a database engine that we have on the client side due to the fact that we will have more data processing requirements on the client side. This means that a much more complex logic will be executed on the client side, and we will have to generate native code, which will be Java in Android and Objective-C in iOS. We should also mention the start, refresh, load events, which previously, in online architecture, were executed on the server side, and they're now executed on the client side by accessing local data. User events continue to be interpreted, with the exception that when offline applications call an offline object, they will do it locally without the need to go to the server to execute it. Another outstanding aspect in this architecture is that both the client database and the server database will have to remain consistent with one another through a process called synchronization process, which we will see in further detail ahead. Now let's see how we do this in GeneXus. We have a property called connectivity support available for all smart device objects, which includes three options: online, offline, and inherit. What do these three options imply? Online is the default option for smart device main objects, and it's the way we've been working so far, including in X Evolution 2, where our application is fully connected. The inherit property is included by default in all smart device objects that are not main objects. This means that they will inherit the behavior of the parent calling it, and the offline property is the one we are most interested in today. So what happens when I set an object's property with connectivity support offline? Suppose we have an application for an event, and a dashboard, set up as main, for which I set up the property connectivity support offline. So what happens immediately afterwards? The next time I execute or compile, a new object called offline database object will be created. This will determine the tables that go to the client's database and also the data taken for synchronization, because it's obvious that the local database will not be the same as the server database, but rather a reduced version of it. So, how do we determine the tables that will be taken to a client's database? I brought this example to make the concept clear, and in line with what we just saw, it's an application for an event. I have a dashboard called Work with Sessions, a Work with Speakers, and a Work with Tweets. So what tables will end up in the device's internal database? For my dashboard, I defined connectivity support offline. Since, as we said, my dashboard is a smart device main object that has the property connectivity support online by default, I changed it to offline. I indicate that, as of now, I want the application to function without connectivity. As we know, we have the object work with sessions, speakers, and tweets. And the property that these three panels will bring by default will be inherit. So the behavior of the calling parent will be inherited, in this case, the dashboard with the offline property. Therefore, they will inherit that offline behavior, and they will be added to the tables they access and to the device's database. That is to say, that the addition will include the sessions, speaker, and tweets tables. And what if I want tweets to only be viewed with internet connectivity, so that users always view updated tweets if they have an internet connection? In that case then, I will need to act on the connectivity support property and set online connectivity support for the Work with Smart Devices panel. By doing this, I'm determining that tweets will only be viewed with connectivity. So the tables taken to the device now will be session and speaker only. We should also point out here that when a table has a foreign key to another table, the table referenced will also be taken to the device. So, let's now see the navigation of this database offline object. As you can see, there's a synchronized event for each table involved. So for each of those events, which are basically for eaches to the table, we will see the conditions applicable. Conditions are used like any other GeneXus object, applied to tables in order to know which data is taken to the device. And why are these conditions applied? For one thing, there may be security reasons where I don't want a user to view all records, and also capacity reasons relative to the device's memory. I cannot take all the records of the server's database to my device because there may be thousands of records and my device's capacity may be exceeded. Due to those two reasons, we will be applying filters. As we saw in previous PowerPoints, we can filter by tables, differentiating or discriminating the tables we want taken from the server's database to the device's database. But, as we will see now, we can also filter by records. And how do we do this? We add a condition. Suppose, in the same example we had, that I only want speakers in my event that I consider important to be taken to the device. That is to say, VIP speakers equals true. So, on the Conditions tab, I add that condition. This will add a constraint to the object's navigation that the for each will continue doing on the speakers table. And also, I add another constraint where VIP speakers equals true. Something important to point out is that we do not have reorganizations, and the database doesn't create every time we modify the data model. Now let's see something about data synchronization. This synchronization will have a process for sending data from our device database to the server, and then a process that receives data from the server to the device database, that is, the client's database. So, starting with the data reception process, there are two ways for synchronization: automatic and manual. In automatic synchronization, we have the following properties at the level of the offline database object. The data received criteria property, by default, will come in and on application launch, but there is also the after elapsed time property. And then there is the manual way, which we will see further ahead. What happens when I set data received criteria with the on application launch property? What will happen is that I will be receiving the data every time that the application does a launch. That is, every time that I pick up the application when the minimum time between receives has elapsed, which is the second property, that's currently set at 600 seconds. A 10-minute period will pass. When I open the application, if 10 minutes have elapsed, then the application will be data receive. What happens when I set the data receive criteria property in after elapsed time? This property is supplementary to the other one, so a data receive will be done every time that 600 seconds have elapsed from the last time that I received data. So it supplements the other property. And this data receive may take place in either one of two ways, which is the last property you see on screen, the data received granularity. It may be received by row or by table. And what's the difference between them? By row, I'll receive in the client database only the server data modified, that is, the modified rows. By table, I'll be receiving the whole table every time that there's a change made. The table will be deleted on the client side for the whole table to be received again. This has advantages as well as disadvantages. With by row, the advantage is that the data transfer from server to client is small because only modified data is sent. The disadvantage there is that there's much processing on the server side, since it has to search for the data that was modified. On the other hand, there's the opposite situation happening in by table. There's little processing on the server side because the whole table is sent upon every change made, but there's a lot of data transferred from server to client. And also, as we mentioned, there's the manual property. What will we decide in the data receive? When we set up the property as manual, the second property we had before, called minimum time between receive, disappears, because the waiting time between receives does not make any more sense since I'll be executing them manually. And how is this done? As shown on screen, with synchronization.receive. When I set the property as automatic, that is, with application launch or after elapsed time, there's also the possibility of using manual synchronization. I'll be able to use, also, the synchronization.receive in user events, some buttons, and so on. This refers to receiving data. Now, let's see the data send, to send data from the local database from devices to the server database. To do this, we have the property at the offline database object level, called send changes. And this includes three options. The default option is when connected, which sends data as soon as I get my device connected. I work in offline mode, and when my connection occurs, that data is sent to the server automatically. There's also the manual option, which validates the data received. Using the synchronization.send method, I'll send the client data when I consider appropriate at the programming level to the server. I could have the when connected option set up and use the manual method of my programming anyway with this synchronization.send method. And the third option is never, for when we don't send client data to the server. A case where this property is used is when we have a personal finance application that includes sensitive data that I don't want on the server. Before we finish this presentation, I would like to mention two things. The first is that when we create an offline application in GeneXus, we install it on the device, and a table called GXPendingEvent will be created. This is where all modifications made offline will be saved, and they'll be in the same order in which they take place. So when we obtain internet connection again, those modifications are replicated in the same order in the server database, which makes the databases consistent with one another. Additionally, in that table GXPendingEvent, we will have associated to each change a state which we will be accessing through the synchronization event API. This is an API that we make available to check possible errors in sending data and to make the necessary decisions in each case. So we could say that this API enables us to make decisions and manage errors relative to synchronization. The other thing I'd like to mention is that everything to be synchronized in my offline applications must be done with business component, and the news and for eaches are not considered. Alright, after clarifying those two aspects, we can now move on to consider conflicts and synchronizations. We'll consider a particular case where we have two devices with the same application installed, and they're both disconnected from the internet for the moment. And we also have a centralized database in the cloud that has no data to begin with. So device 1 does an insert of country Uruguay and of country Brazil with their corresponding cities, Porto Alegre and Montevideo, in the country tables and also in the city tables. We must point out that both the country ID and city ID keys are auto-numbered. This is important in this particular case where we'll be managing conflicts. As we said, device 1 does that insert of Uruguay, Brazil, and device 2 does an insert of Argentina and Paraguay in the same tables, also with tables country ID and city ID auto-numbered. What happens when those two devices are connected to the internet and must be synchronized with the centralized server database? Suppose that device 2 is the first one connected and synchronizes its data with the server. Then, it will send Argentina, Paraguay, Buenos Aires, Asunción to the server's tables. When device 1 tries to synchronize, there will be a conflict because it will be trying an insert in the same table with the same ID. Therefore, when it calls for Uruguay with country ID 1, it'll find that country ID 1 is already Argentina, as entered by device 2. So, how is that conflict resolved? The server will solve this automatically. Since the keys are auto-numbered, it continues adding those numbers, taking Uruguay and Brazil, and assigning the value following the last one existent. So because Uruguay 1 and Paraguay 2 already existed, it'll change the ID of Uruguay to make it Uruguay 3, and the same applies to Paraguay 4. The other interesting thing to note here is that modifications may also be done in cascade. That is, Uruguay with ID 3 and Brazil with ID 4 are also modified on the city table. Because it has foreign key, they're modified there for consistency. And what about the data I had on my device, Uruguay 1 and Brazil 2? What it does here is a backwards modification. After the modification on the server is ready and consistent, it makes the modification in devices, making the whole environment consistent with the final values you now have on screen. So, this is how conflicts with auto-numbered keys are resolved. Now we'll go into some considerations regarding prototyping and GAM. In regards to prototyping, I'd like to say that KBN will not be available for testing offline applications. What does this mean? Since we'll be generating our offline applications in complex logic, which imply the generation of programs in native code, Java and Android and Objective-C in iOS, the KBN only interprets metadata and will not be applicable for executing this type of logic. It's therefore not applicable for testing offline applications. We will then have to compile and execute those applications on the devices. Regarding the GAM, I wanted to mention two things. One is that credentials are kept on the server due to security reasons. We don't take user credentials to device databases. And as a result, the other thing to mention is that the login is done online only. I will only log into my application when I'm connected to the internet. In third place, we could say that user authentication may be done only online, but if we lose the connection after the authentication takes place, we may continue to access our application screens offline. And one last thing to mention is how we convert the applications we use to work with in X-Evolution 2, online applications, into offline applications in X-Evolution 3. As we mentioned before, what we must do is change the connectivity support property to offline. By default, this property is set to online. After changing it to offline, we will select the way in which we want the data to be sent and received. As we saw in previous screens, we have the options of automatic or manual, and whether it's by row or by table. We have to set up those options, and also remember that it's necessary for all changes we want sent to the server database must be done with business component. So, bearing all that in mind, we'll also apply filters. As you may recall, we can decide which tables we want sent to the device's database, and from those tables, which records we want sent to us. So we apply those filters, and then do a rebuild all of the main object. We should also remember that there are some non-compatible data types. There are some examples like mail messenger, cookie, Excel document, and others. You can find further information on this topic at the wiki, but the main conclusion to draw now is that changing our online applications to offline is quite easy to do. Well, this about wraps up everything I wanted to talk about today regarding offline smart device applications. I welcome you all to download Evolution 3, test it, and benefit from all the advantages we showed here.